This section is called Simple Patterns of Chemical Reactivity. If we could do this in person, it would be so much easier, but I will try my best here. When we have something called a combination, it is when we go to form only one product. Think about what you taught yourself in Chapter 2. Magnesium is a +2, oxygen is a -2. So when these two items come together, they will form MgO, and I will just tell you today that it is a solid. But you should be able to predict the identity, especially once we get to Chapter 4. If we look at the next example, N2 plus H2, nitrogen has a common oxidation state of -3. Hydrogen is a +1. That would have us produce NH3, and I'll tell you that that is a gas. What we're going to teach in this section is how to balance. So I'm just going to place a 3 here and a 2 here, and we will have a balanced equation. These are examples of combination. Another thing that can happen is decomposition. And I wrote them in here because honestly, at this point in the course, you really don't know that those are the two products. So decomposition is when you form two or possibly more products. Here, calcium carbonate decomposes to make calcium oxide and carbon dioxide gas. Another example that you'll run into in biology is peroxide decompositions, and that forms water and oxygen. Again, learn what these are, but it's not something you came knowing. The third type of chemical reaction is a combustion. And when we say excess oxygen, people often don't write it that way. They just say CH plus air, and that will always make carbon dioxide plus water. Why did I not give the formulas? Oh, there I did one of them. Because I want you to think about what is really going on. If this are always my two products when I do a combustion, how are we going to balance it? There is a method. First, we're going to look at the carbon. We see there are 3 carbons as reactants. It says we need 3 carbons as products. So what we're going to do is we're going to put the number 3 in front of CO2. Next, we're going to look at the hydrogen. We see there are 8 hydrogens as reactants, and that means we need to see what to do with the products. At this point, we only have 2 hydrogens as our product. We need to have 8, so what we will do is we will place the number. What number will we place there? We will place the number 4 in front of water. So let me rewrite this. We have C3H8, we have oxygen. It's going to form 3 CO2s plus 4 H2Os. Now, the only thing we haven't balanced are the oxygens. I see on the right we have 2 oxygens as reactants, and on the product side we have 6 plus 4 for a grand total of 10. Oxygen comes to us in units of 2, so in order to balance this, we would put the number 5 in front of the oxygen. And how would this be asked on an exam? They would say, what is the sum of the coefficients of the reactants? Now, I don't want to say it's a trick, but know that there is a non-written down number 1. So if I were to sum what are the coefficients of the reactants, my correct answer would be 6. Now here is another example. It almost looks the same. We have C3H8O and it's undergoing a combustion. We know that it will make CO2 and it will also make some water. I'm going to do the same thing I did last time. I notice there are 3 carbons. I'll put a 3 in front of the CO2. I see that there are 8 hydrogens. I'll put a 4 in front of the water. So what I have left is to balance my oxygens. I have 1 coming from C3H8, and I have the 2 written there for a grand total of 3. On the product side, I have 3 times 2 and 4 times 1. 4 plus 6 plus 4 equals 10 oxygens. Now, I'm going to just play it this way because it is the best way to explain it. I'm going to subtract 1 oxygen. That's the one that comes to us from the C3H8O. That gives me 9 oxygens left. That says I can put a 9 halves in front of the diatomic oxygen, because that will give me 9 oxygen atoms. So let me just continue to rewrite, and there is my equation. Now there is an issue. We cannot have fractions in chapter 2. We must have whole numbers, okay? And again, I'm saying chapter 2 because things are going to change. So what I'm going to do is I'm going to multiply this whole reaction by 2. And I'll come up with 2C3H8O plus 9 oxygens going to form 6 CO2s plus 8 H2Os. Think about what we said, the sum of the coefficients of the reactants. Here the answer would be 11. So again, that's what you have to be prepared to do. Trial and error is another best way to put what's going on. Leave the hydrogen and oxygen for the end. If I look at this example, 1 phosphorus, 1 phosphorus, we are okay. If I look at the chlorines, I see 3 of them. That says for me to have 3 chlorines, I need to put a 3 in front of the HCl. So again, trial and error by inspection. I know I need to balance the hydrogens and the oxygens. I have 2 hydrogens and 1 oxygen. On this side, I have 3 plus 3 for a grand total of 6 hydrogens, and I have 3 oxygens. So I need to look at this and say, what can I do to make this work? Notice if I multiply the number of atoms by 3, I will then have a balanced equation. So it would be PCl3 plus 3H2O going to form H3PO3 plus 3HCl. Can't memorize this. Please practice so you get you just get a feel for how these things need to go. Here's another one. Calcium oxide plus phosphoric acid going to form calcium phosphate and water. Again, take a look at the numbers. Calcium, here is the number 3. That means I will need 3 calcium oxides. P, phosphorus. Take a look over here. There are 2. It means we're going to need 2 H3PO4. We're not going to touch that calcium phosphate. Ca3PO4 So what we're not going to need to do is balance the waters. And that's all I'm going to do here. I'm going to look at the oxygens. There are 3 plus 2 times 4, 8 for a grand total of 11. And I'm going to look at the hydrogens. There are 2 times 3, which is a grand total of 6. When I look at this other side, I have the water, and I'll count my oxygens again. I have 8 plus only 1 for the water to give me a 9. And when I look at the hydrogens, I just have a grand total of 2. What can I do to make this balance? Well, I need to multiply on the product side by a factor of 3, and that will bring me up to date with the numbers of oxygens that I have. 8 plus 3 is 11, and 3 times 2 is equal to 6. If we were live, I'd be walking through the room, I'd be going up and down the aisle, I would be pausing, I would let you try it yourself. It's just a lot more difficult trying to teach this part online. One last piece, potassium nitrate, that's the second example, goes to form potassium nitrite and oxygen. Again, notice, we are giving you the products. You don't have to worry what it's going to form. You just have to think about how to balance it. So let's start with the potassium, 1 on each side. Let's now look at the nitrogen, 1 on each side. Now let's look at the oxygen. 3 oxygens on the reactant side, 2 plus 2, 4 oxygens on the product side. The easiest way to talk about this is to say, let's make it 1/2 O2. Then it will simply be 1 oxygen. Can't have any fractions, have to multiply this by 2. So we will have 2KNO3 going to form KNO2, 2 of those, and an oxygen. Again, ask questions if you don't follow, and please practice. So what's left? Is there anything relevant about what's going on here? Well, I've written an expression here where we have sodium nitride going to form sodium and nitrogen gas. All the airbags in the cars have this reaction that has the potential to occur. People have used sodium nitride. It's not the best, so they have a different proprietary material. But what they did to cut costs was instead to use ammonium nitrate, because that will also produce nitrogen gas. And so what happened, well, think about what just happened in Beirut. They had a warehouse full of ammonium nitrate. It is explosive when it decomposes. And that's one of the reasons that these airbags started to explode. There's a lot more chemistry going on. What I included here was the actual stoichiometric conversion. When your airbag explodes, it produces about 50 liters of nitrogen. I hope you've never seen one, but if you do, that's really the amount of nitrogen that is given off, enough to protect you. So again, balancing equations is extremely relevant, and we will actually do the ammonium nitrate heat given off when we get to chapter 5, okay? So what else do you need to pick up out of these first 3 chapters? Well, understand how to apply what's called a particle diagram. That's these pictures. They did not exist when I was in college, but they feel they're important now. I'm not going to work this one here because it's the end of your textbook chapter 1.1, where you need to identify elements, compounds, mixtures of elements, and mixtures of compounds. I think you can handle that. What I want to do is, again, reinforce. You know what a chemical change is from chapter 1. But if you look at a particle diagram, can you discern which is a physical change and which is a chemical change? Again, we're going for insight. You know, we told you what these things are. So what it looks like to me here is we have a solid. What it looks like to me here is we have a gas. And that's one of the reasons I chose Alex. I wasn't thrilled that your textbook just did it once. Alex does it over and over and over so that you can see what's going on. Well, a change from a solid to a gas, that is a physical change. It is not a chemical change. When I look at the solid in part B and I see what has happened in the product, I definitely have gone from some solid, and let's just say this is an A2B2. They didn't tell us what it was. What we've made are A2s and B2s, so this is definitely a chemical change. Again, insight is what we're looking for. You've got to know your facts, you've got to think of the method, and then you have to apply it in a situation. The last one is sample exercise 3.1. It comes from our current chapter. And it says, write the chemical formulas and a balanced equation. If red is oxygen, well, if I look at red and oxygen, I see an O2. What am I going to call this thing? Well, I'm going to call this nitrogen oxide because it's the naming we learned in chapter 2. So it looks to me like O2 is reacting with NO, and what is it forming? Well, it's forming, it looks to me like an NO2. If I look at this equation, it is definitely not balanced. So there's many different paths you can follow. I'm just going to count. I have 1, 2, 3, 4 oxygens. If I count them carefully, I have 8 NOs. If I go count my product side, I have again 8 NOs. That is a balanced equation, but what we want are the smallest coefficients. So that's going to take us to oxygen plus NO goes to form NO2. I guess we could have done it either way. So here's my number 2, and now I have a balanced chemical equation. So please practice, please ask questions.